Welcome back. Today we're going to talk about conditional probability. I'm going to assume you already have some knowledge of basic probability, empirical probability, theoretical probability, and start where that leaves off. The idea of conditional probability should be intuitive, though if we strip away the mathematical language. We want to know if thing A happens, what is the probability that thing B also happens? One example, imagine you're considering participating in a protest on the National Mall. Your mother's worried that you might be hurt or arrested because she's seen videos of the riots and the arrests and the hooligans on the TV. To reassure her, you could look up the number of injuries and arrests from past protests on the mall, maybe even look up the estimated attendance to try and show her it's unlikely these outcomes would happen to you. But ideally, you don't just want to know how many people have been arrested or hurt, you want to answer the question, if I attend, what is the probability that I will be injured or arrested? Or even better, the question, am I more likely to be injured or arrested if I attend than if I don't? The size of the groups makes all the difference. So if 5 arrests were made on average, but the mean protest size was 20, your mother probably has a good reason to be concerned. But if the mean protest size is 100,000 people and only 5 people are typically arrested, you'd actually be more likely to get arrested not going to the protest than going to it. So the easiest way to do this, if you're working with empirical or theoretical probabilities, that is, if you know the number of cases, the number of possible events, is to make what's called a contingency table, a crosstab, or a cross-tabulation. For our example, we need to know 4 things. How many people protested? How many people didn't protest? That is the population that we're drawing from, the number of possible events. How many people were arrested at the protest, and how many people who were arrested that could have protested but didn't. So I've gone ahead and made a crosstab table here. You can see we've got about 197 protesters, 2 of whom were arrested, and 321 million and change residents of the U.S., about 29,500 of which are arrested on an average day. These numbers for the U.S. are true numbers from 2015. These numbers are completely made up. Unfortunately, by themselves, it's hard to make heads or tails of these because the scale's so different, right? We can't just eyeball it and say, oh yeah, that one's more or less. But we can calculate all the necessary probabilities to decide whether we're more likely to get arrested if we protest from just these numbers. First, though, let's step back and talk about terminology and symbols. In life, we might talk about the probability of this or that, this and that, or this if that. Mathematicians have words and symbols for each of these. The total sample pool, which in our case is people in the US, can be divided into what are called sets of cases fitting certain conditions. The mathematical notation for a set uses curly braces, and the numbers or ID numbers or cases are separated by commas within them. So this is set A is 1, 2, 3, even numbers. Cases 1, 2, and 3 perhaps. Set B is 2, 3, and 4. Now, what if we want to put these together? There's a number of ways to combine them, right? So the union of 2 sets, represented by this big wide U, union of set A and set B, is all the cases that are in one or both of them. So in this case it would be 1, 2, 3, and 4. The union of A and B would be the set of all cases that are in at least one. If we flip that U upside down, so it looks like a rainbow, we have an intersection instead of a union. The set here is the cases that are in all of them, or both of them. So in this case, it would only be 2 and 3, because 1 and 4 are each only in one case. The terminology here can be confusing, though, because the word union is usually about combining, but the word or that I said, it's in one or the other, is about choosing. Likewise, the word intersection is a place where you make a choice, right? You come to a stoplight, an intersection, and you have to choose, do I go left, right, straight? So you might think or, not and. But there are ways to remember these. One is to remember that this and other set theory words you can always ask, what are the requirements for membership in this new set? If we ask what the requirements of membership are for union, the answer is cases in one or more constituent sets. They're unified. For the intersection, the answer is just the more. The road metaphor can help too, because you could say there are two paths that are equally good to get between 2 points. You could drive on one or the other, but they may never intersect. And we can also try and understand this graphically. If we were to draw 4 overlapping sets, like this, let's see, we've got red, we'll have green, and then we'll take our black pen. This side is A, this side is B. So we've got 4 sets overlapping between 2 different types of categories. Every case is either an A or a B, and every case is green or red. So the union of A and B then, A union B, is everything. The intersection of A and B is nothing, right? Because there's no place where those two overlap. But what if we said the union of A and green? Well, then we could find that the union of A and green would be this, because they're in A, and this. So we're saying it's either A or it's green. The intersection of A and green instead would only be this. It's the place where it's both A and green. So let's get back to our original question. Is there more risk of arrest when you're participating in a protest? Put in terms of probability, the question could be rephrased. Is the mean probability of being arrested higher when participating in a protest than in the general population? To answer that, we need one more thing. We need conditional probability. That's the last piece of notation we're going to need for today. So if this is the union, or this is the intersection, and now we want A given B. That vertical bar can be read as given, or you can think of it as an if. If B, what's the probability of A? Going back to our contingency table, we could start to work out some probabilities, right? We could calculate the probability of protesting and being arrested. That would be 2 out of the entire population, the sum of all 4 cells. That would be the intersection. We could calculate, there's no real reason, but we could calculate the union of, say, being arrested or protesting. So it would be everybody who's not in this great big cell. But what we're really interested in is the conditional probability of being arrested if you're protested, which would be simply the probability of something given something else. The probability of condition A given B is equal to the probability of A intersecting B divided by the probability of B. That is the probability of the given condition being true. So if this, what's the probability of that? It's actually, so applying this to this case, we would have the probability of arrest given when protests is 2 over 321 million and change divided by 195 over 321 million and change equals 2 divided by oops, I'm sorry, 197. We've got to add those two people in, so 2 out of 197, which you probably could have intuitively worked out up here. But by talking about it in terms of conditional probabilities, we're getting ready for the next steps in probability and statistics, thinking about conditional relationships. What is the effect of x on y given a set of other x's, for example? The key to a conditional probability is just getting the correct denominator. So a couple more things. The percent of cases in a specific row that fall in each column are also called row percents. So if we were to calculate the row percent here of that, instead of putting 2, we could put whatever 2 out of 29,500 works out to in percentages. This would be like 99.999%. This would be like 0.001%. You may also hear the term column percents. That would be the percentage that 2 is out of 197, the total in the column. They're basically the same thing as we just worked out, at least in the 2 nominal variable case. So to put it in terms we've used before, the population we're interested in is only cases falling in the given condition. To answer our question then, if we calculate the conditional probability of arrest for those who don't protest, and compare it to what we just calculated for those who do protest, we'd see that Mom was at least not completely off base. It does appear to be safer to stay home. The 29,500 out of 321 million, that's 1 in 1,000 or so, as opposed to 2 in 200, give or take. There are ways to formally test whether those differences are statistically significant, but we'll save that for later. For now, the main goals of this section are twofold. First, you should be able to recognize the terminology and notation of set theory if you come across it. Second, you should come away with both an intuitive and formal understanding of how to calculate conditional probabilities. You should be able to connect them. That in turn will lay the foundation for thinking about conditional relationships more broadly. That is to work toward answering the question, is the relationship between x and y conditioned on some other variables? That's all for now. Thanks for watching.